Right. Well, hello, everybody. My name is Adrian Bowyer, and I used to be academic at the University of Bath in the United Kingdom. I retired about 12 years ago. I did research projects while I was there, but one of them is the one that I'm going to talk about now, which is a research project into 3D printing. And in particular, it's to do with a 3D printer that copies itself, as you can see on the first slide that I'm showing. I had the idea to do this about 20 years ago, and we set it up as a project, and then the project progressed, and I'm going to tell you a little bit about what happened and how it works. Let's start, though, with 3D printing. I'm sure some of you will know how 3D printing works, but let me explain it for those of you who don't. There are many different 3D printing technologies, but the one that I'm going to be concentrating on is conceptually very simple. It's a computer-controlled glue gun. So you have a feed of plastic, which is labeled A here, and that feed of plastic in the form of a filament, like a rather thick fishing line, is driven downwards through those two little rotating gears that you can see into a chamber which is heated, where it's melted, and the plastic comes out of a nozzle a little bit like a very thin stream of toothpaste. And so far, as you can see, that's exactly like the way that a glue gun works. But what you do is you then print with that plastic by moving the hot head, which is extruding it, around over the plate, which is labeled E in the diagram. And you basically scribble the bottom layer of the object that you want to print. And then you move the plate E downwards a tiny little bit, and you scribble the next layer, and you scribble the next layer, and so on, until you've finished up with a complete three-dimensional object. Now, as I'm sure you'll be able to see if you do that, there are going to be bits of a problem where you've got things that overhang. So, for example, you can see a head being printed here, and thin is an overhang. And if you imagine that, you're trying to print in thin air. So in addition to printing the object itself, the machine also has to print what's called support material, which is some little supports that go underneath the bits that overhang, and you can see those labeled D on the diagram. And those are designed in such a way that you just break them away with your fingers when the whole process is finished. So you've got something that makes three-dimensional objects. You can just plug it into a computer, and if the computer's got a three-dimensional design, you can just print it straightforwardly without any human intervention. Okay, so my university got some government money about 25 years ago, and they gave it to me to spend, which was maybe foolish of them. Anyway, they gave it to me to spend, and I bought a couple of commercial 3D printers. And as soon as I got one, I realized that this was potentially a machine that was so versatile in making shapes that it could print a copy of itself. It couldn't, the commercial ones couldn't make copies of themselves, but we could design a 3D printer that was able to copy itself. Now, it doesn't copy every last bit of itself, but it copies an awful lot. And here's an example of a self-copying 3D printer design by a guy called John Mullack. And in that picture, you can see the plate on which the printing happens, and you can see the hot head, which is like the glue gun, which is the blue object with the cables going to it. And everything in that picture that's either blue, red, or white was printed in a machine like the one you can see. And so you can see that the vast majority of the machine is actually made by another machine like itself. So we've got a machine that copies itself, and I'll say a little bit later on about how it gets distributed and how people obtain it and so on. But how did I come up with the idea? What was it that prompted this? Was it some engineering consideration? Well, no, it wasn't, in fact. What I was thinking about was, oh, sorry, before I get on to how I came up with the idea, I should say something a little bit about the name, which is RepRap, short for Replicating Rapid Prototyper. Rapid Prototyper is what 3D printers used to be called when I started the project. And we decided to give it all away free. And the reason we give it all away free, by giving it all away, I mean, we give all the designs away free so anyone can download it. When you've got the designs, of course, and you've got any old 3D printer, you can then use the designs to make yourself another one, is because when you've got something that copies itself, you can't really protect it anyway, because if you try and patent it, for example, you're just saying to people, you're not allowed to do with my machine the one thing that it's designed to do, which is rather silly. And because we gave it all away free, we got volunteers on the project from all over that came to work on it, because it was an open source project. And as a result of all that work, most 3D printers in the world are now either RepRaps or REP derivatives. And so there at the top right is another example of a design from machine, rather simpler than the one I showed earlier, made largely with 3D printed parts and steel rods, which is something that's very easy to obtain almost anywhere. Okay, back to how I came up with the idea. I wasn't really thinking about engineering at all. I was thinking about biology, and in particular symbiosis and what biologists call mutualism, though most lay people just call it symbiosis. Biologists call it symbiotic mutualism. Now, the example of this phenomenon that everybody has heard of, and we all get taught it at school, is the symbiosis between the flowers and the insects, like bees. And the way this works, again, we're all taught at school, is that the plant must move its pollen to another flower, and of course plants can't move, and the bee needs food. And so what happens is the plant pays the bee with nectar, food, in order for the bee to move the pollen to another plant. And so the bee gets a meal, the plant gets to reproduce, it gets to set seeds, and both species benefit from this arrangement. And they're in what the biologists call an evolutionarily stable strategy. That is to say, they've evolved to the position where they help each other, and that position is one where any mutation or change in either the bee or the flower makes them less likely to reproduce. So hence it's what's called evolutionarily stable. It lasts for a long time. And indeed, this particular evolutionarily stable strategy has lasted right since the time of the Jurassic era. Okay, but human beings get involved in these sorts of strategies and symbioses. And in fact, farming is a good example of our symbioses. For example, cows and corn must have somewhere to grow and to reproduce, and people obviously must eat. And so we treat the cows and the corn rather as the bees treat the flowers. The cows and the corn get to reproduce in the fields that we provide, and they in return provide us with food. Now, of course, in order to provide us with food, they end up dying, but from an evolutionary perspective, they're extremely successful species because they get to reproduce an awful lot, because they have a symbiosis with the most powerful organism that has ever existed. And once again, farming is an evolutionary stable strategy for us and for the species like cows and corn that we collaborate with in our farming. And RepRap, the idea of replicating 3D printer, came about as a consequence of looking at that symbiotic idea and seeing how it could be moved into engineering. The machine, the self-reproducing 3D printer, needs to be assembled. It can't assemble itself, so it needs help from people in order to reproduce. And there is another picture of the machine we just saw. That particular machine is called Mendel. And people need goods. We need everyday things like combs and coat hooks, and we need to make perhaps a cat flap for our cat to come in and out of our house, all sorts of things. So the RepRap machine needs to be put together. People need goods. And there's a symbiosis between the two, in that the RepRap machine pays people in goods because it can print goods for them, and the people then will help it to reproduce. And the idea was that that would be an evolutionarily stable strategy in engineering for both the 3D printer RepRap and for human beings. Okay, so anyone with a plant can grow a seed for a friend, and anyone with a RepRap can make another RepRap for a friend. And there's a picture of the very first two machines. And the first time the machine on the left, built using a conventional 3D printer, not a someone, the first time the machine on the left reproduced was on the 29th of May in 2008. So that's me on the left, and the bloke on the right is a chap called Vic Oliver, who's a New Zealander who was one of the volunteers on the project. And the machine on the left printed all the parts for the machine on the right. So the machine on the left is the parent of the machine on the right, which is its child in a way, in just the same way as an insect is the parent of the egg that the insect lays. And this idea has rather taken off. So, for example, here is part of Josef Prusa's RepRap farm. This is a company in the Czech Republic that has large numbers of RepRap machines arranged in a warehouse, and you can see just a small part of the warehouse there. And these machines are working 24 hours a day, days a week, making parts for more machines, which Prusa Research then package up in boxes and sell all over the world. So you've here got a farm, but the farm is now not breeding animals, it's not breeding plants, it's breeding 3D printers that are capable of copying themselves. So the idea of a self-reproducing 3D printer has rather taken off, and here's an example of one of the ways in which it's done so. This is part of Josef Prusa's RepRap farm in the Czech Republic, a small part of a very large warehouse where he has rows and rows of RepRap 3D printers. And instead of the farm having animals or plants reproduce, this is a farm where 3D printers reproduce. All these machines are printing parts for more 3D printers, which he then puts in boxes and sells all over the world. And there are other companies that work in the same way. For example, Lulzbot in the United States have the same strategy. And it's turned out to be very successful. Okay, so I'm that 3D printing was a very versatile way of making things, and that was the reason why I thought finally we've got a technology that is caping itself when I first got to use a 3D printer. Why is it that 3D printing is so good at making things compared to other technologies? And I say here that 3D printing is the second most versatile manufacturing method we know. The most versatile manufacturing method we know is actually the one that we've just talked about, namely animals and plants growing. That's an extraordinarily versatile way for them to make themselves, and works even better than 3D printing, is even more versatile. But 3D printing, of all the ways of making things that engineers have ever come up with, is the most versatile. Let's look at how difficult it is to make. And on the left on the picture there is a conventional manufacturing machine. It's a computer controlled CNC mill, in fact, which is basically a controlled electric drill. The little orange head there has a spinning cutter in it, which it can move in 3 dimensions. And if you put a block of metal in there, it can cut shapes out of that metal under the control of a computer. And as you've seen before, a RepRap machine is a computer-controlled glue gun. And there's a picture on the right of a different type of RepRap working to print a vase. The green vase is being printed on the surface of its bed there. So why is the process on the right more versatile than the one on the left? Well, to answer that question, we have to look at how shapes can be complicated, because always when we're making something, we're concerned with the shape of the thing that it is that we want to make. So what does simple and complicated mean when we talk about solid shapes? Well, here's a picture drawn for a book many years ago by an old friend of mine, a man called John Woodcock. And he pointed out that complicated means different things for shapes depending on how you look at the whole question of complexity. So we've got a sort of 3-dimensional space here. Along the bottom axis, where it says combinatorial complexity, is the way that you'd think complicated would be most likely to go, namely more bits. So we've got a simple shape on the left with a single hole in it. On the right, we've got a complicated shape with many more holes in it. The vertical axis, the y-axis if you like, is dimensional complexity. The object bottom left is essentially a flat object. It's got some thickness, of course, but its features are all 2-dimensional. If we move up a dimension into 3 dimensions, then we get more complicated shapes again, because 3-dimensional objects are more complicated than what are essentially 2-dimensional ones. And the final axis, front to back in the diagram, is what's called analytical complexity. That is to say, the mathematics that describes the shapes gets more complicated as you move further back along that axis. The object, again, bottom left, is composed of straight lines and bits of circles, whereas the tap fitting, top left, is composed of much more complicated surfaces, which the algebra of which is much more difficult to write down. So we've got all these 3 ways in which things can be complicated. And let's look at how that impinges on how they get made. Well, here's an example of the 2 processes again. On the left there, we've got the essence of the computer-controlled electric drill. You've got the cutting tool, which is the yellow tip of the object in the left and the picture on the left. That's basically a spinning drill bit, and that's moved around in order to cut out, well, in this case, it's the air compressor from a turbocharger in a car. And that used to be a solid block, and it's being cut out by that tool, which is moving around. Now, in order to do that, the machine, rather surprisingly perhaps, works not in 3 dimensions, but in 5 dimensions. And the reason is it moves up and down, left and right, and front and back. But the angle at which the cutting tool is can also be rotated about 3 directions. Now you'd think, now we've got 6. We've got up, down, left, right, and front, back, and we've got 3 rotation directions. But in fact, the rotation of the cutting tool itself counts as one of those dimensions, so we subtract that dimension, and we end up with a 5-dimensional problem to solve if we're going to use that technology to make the, well, in this case, the turbine blades. Now, what about 3D printing? Well, 3D printing works always in layers. So at any time when the 3D printer is working, we only have to consider a 2-dimensional problem because we're looking at a slice through the object that we have to make. Now, one of the things about computers dealing with any sort of geometrical problem is that the more dimensions you have, the much more difficult the problem becomes. And because conventional manufacturing increases the number of dimensions from 3, whereas 3D printing reduces the number of dimensions from 3 down to 2, 3D printing can make incredibly complicated shapes really very easily indeed. And the technology is complete in the sense that there is no shape that it can make that we can't tell a computer to tell the technology to make. In other words, there is nothing that's physically possible for the machine to make that the computer can't instruct it to do so. So that's why 3D printing is so versatile. Okay, let's have a little look at economics, and in particular the idea of economies of scale, which is a very old idea in economic theory. On the picture on the left there, we've got what is essentially a 17th century iron foundry, which is a blacksmith's workshop. We've got 2 people working in it, making horseshoes and hinges for people's gates and all that sort of thing. But by the time history had moved on a little bit, by another 2 centuries, we had foundries, which were large factories for essentially solving the same problem, making iron objects out of by bending bits of metal and having heated them. And because the iron foundry has got the division of labor in it, so some people can do the accounts and some people can do the advertising and some people can keep the furnaces burning and so on, it's much more efficient than the system on the left. And the whole idea of this is called economies of scale. When things get bigger and more organized in factories, you can make things much more economically than you can if they're made on, as it were, an individual basis. Now, this idea, the idea of economies of scale, doesn't extend forever. It actually goes into reverse when you've got real and simple technology. Here's a couple of examples of the technology of economies of scale, the economics rather of economies of scale going into reverse. Top left is a picture of a 19th century laundry where everybody in the city used to sell their clothes to be washed. It was a factory, if you like, for doing laundry. Now, we don't have those anymore because everybody's got a factory, everybody's got a laundry robot that sits in their kitchen, and it's the object illustrated top right. And because that's so simple and easy to use and is not horrendously expensive, it's replaced the economies of scale on the left. And an interesting observation perhaps about the washing machine is that we spend maybe $300 or $400 on it, but we're quite happy for it to sit in our kitchen completely idle for 90% of the time, even though we spent that money on it, because for the other 10% of the time it saves us a great deal of effort and trouble and money. Power generation. Economies of scale cause human beings to build power stations like the one at the bottom left. But increasingly, people are generating their own power because the technology to do so is cheap and simple. Solar panels are, in fact, the cheapest form of energy generation that humanity's ever had access to. And so power generation is beginning to get distributed and is no longer subject to the general law of economies of scale. Okay, so today, most people have their own CD pressing plant, and they have their own photographic lab, and they have their own press. Of course, their versions of those things don't look like the objects you can see there. They just do those things using their computer. And so because distribution gives convenience and robustness, all of these previously centralized economies of scale type technologies are things that people have taken into their own home. Well, given that we can do all of those things in our own home, why shouldn't they have their own factory in their own home? Why shouldn't we replace general manufacturing factories by a 3D printer in people's homes that can print not everything, but many of the things that they want? And if we're going to do that, let's make it a factory that makes more factories so that other people can have a factory of themselves if they know someone who's already got one. Okay, well, self-replication is inherently distributive. It makes it very easy for people to obtain a technology, and it works against the concentration of things, as in the economies of scale. And the reasons for that is because it's self-replication in just the same way as plants and animals self-replicate when we farm them. Okay, finally, here's the original RepRap machine that you saw in the picture a little while ago, which is now in the Engineers Gallery in the London Science Museum. I have to say it feels slightly strange to be a person who's still alive and yet has got one of their creations in a museum, but there it is. Anyway, the very first machine we called Darwin because it was the origin of the species. And that's much all I want to say. If you want to know more, point your phones at that and take you to the website for the entire project. Thank you very much for listening.